we want to try to write a set of equations or an equation for displacement and slope in this problem. Now that's a pretty simple problem. If I ask you to draw the shear force and bending moment diagram for this problem, you're going to smile.
Oh, yeah.
If I ask you to write the equations for shear force and bending moment, would this be a hard problem? No. So, well, then let's dive in and see how easy it's going to be.
All right. Sounds like
Can I write an equation that is continuous across the whole structure for moment? No. I have one that's going to be good for what? Over the first half, and then another one that's going to be good over the second half. So let's do that. I'm going to first cut the structure somewhere between 0 and L, probably look to the left, and then I'm going to cut it somewhere over here from L over 2 to L and probably look to the right. In both those cases, well, for both those cases, I'm going to need my reactions. I don't think this is going to be hard to do, but I'll draw it anyway. So there's my free body diagram with the point load P in the middle and my reaction on the left. I'll call it AY. And on the right, BY. And as shown here, those will be lengths of L over 2. I think you can probably already see what it's going to be, but I'll go ahead and make the calculation quickly. If I sum moments at B and make sure my structure is in equilibrium, what do I have? I have a positive moment created by P times a moment arm of L over 2. And then I have my AY reaction creating negative moment with a moment arm of L. So surprise, surprise, AY is P over 2. If I sum forces in the Y direction, what is BY going to be? It's also going to be P over 2. So I'm going to shortcut that a little bit. I think you can get that. We are going to have some challenges here. So let's start with the expressions when x is between 0 and L over 2. So if I look at that free body, there it is. It's a length L, and my reaction is P over 2. And right now I'm only really interested in my moment. Obviously there's a shear force there, but we're not going to consider shear right now in our equation. So if I sum moments at this cut, what do I get? Well, the internal moment M is positive. The reaction force P over 2 at a moment arm of X is negative. So the moment is equal to Px over 2. Now how can I check that? When X is between 0 and L over 2, that's my range, do I know anything about the moment in that range?
It's 0 A.
Yeah, A, it's a pin, external pin, so I know when X is equal to 0, the moment should be 0, and that checks. I can't check it anywhere else. I surely can't check it at X equal L, because it only goes to L over 2. So let's go to the other side. Let's look at it from L over 2 to L. So in that case, I'm going to look at the right-hand side, which we know it'll be a distance x to the cut, and then the remaining little piece will be L minus x. On the right-hand side, I'll have my force P over 2, and then there's positive bending moment. So again, I'll sum moments at the cut, make sure it's 0, and when I do that, my internal moment here is negative. the moment about the cut from the reaction load is positive. So it has a force of P over 2 and a moment arm of L minus X. So it looks like the moment here is going to be P over 2 times L minus X. Can I check that? Do I know the moment anywhere between L over 2 and L? At B. So that's at X equal L. I put in X equal L, it is 0. Is there something I can check between these two? Do they share a point? They share L over 2. There's not an applied moment there, so the moment shouldn't jump. So I put L over 2 here, I get PL over 2. I put L over 2 here, I get PL over 2. So it seems the equations are valid. Now I'm just going to subscript this one 1 and subscript this one 2. Region 1, region 2. Right? Now what do? Well, I need to integrate this guy. So I'm going to come over here and I'm going to say the slope in region 1 will be the moment divided by EI integrated. So I'll pull out my P over 2 and I'll have a P over 2EI, and then I'm just integrating X dx. So that's just going to P over 2EI. That'll be X squared over 2. And my first integration constant, C1. And I can continue. I know that the displacement in region 1 will be integrating the slope. So let's integrate that. So I get P over 2EI X cubed over 6 plus C1X plus C2. Kind of what we've been doing so far. Except that's not but half the problem, right? What's the other half? Well, I got to do it for section 2. So let's do the same thing. So the slope in section 2 is going to be P over 2 and then divided by EI, so P over 2EI, that's the same. And then I'm going to integrate L minus X dx. So just a lot of writing the same stuff down here. So P over 2EI, and then I'll integrate that, so I get LX minus X squared over 2. And then a new integration constant, I'll call it C3. And then I can integrate the slope to get my displacement equation, which is going to be P over 2EI. And now integrate the rest of those terms to be LX squared over 2 minus X cubed over 6 plus C3X and a new integration constant, C4. My hand hurts. Now what do? How many constants do I have? 4. So that means I need 4 conditions to match it. How many do I have? We are. We're going to actually make some up. Wow. Now we do know what? From 0 to L, what do I know? I know that at x equals 0, what's the displacement? 0. At x equal, y at x equal L is 0. There's 2. In fact, I'll just number them. There's 1, And there's 2. So what other 2 things can we come up with? And I'll point you back to the fact that we match the moment equations at the common point. What else can we match at the common point? Should the slope suddenly change when I predicted it L over 2 from region 1? Would it automatically change and bend when it goes into region 2? No. So that's going to tell me, where can I write this? That the slope in region 1 at x equal L over 2 has to equal the slope in region 2 when x is equal to L over 2. So there's my third condition. What else do I have? I match the slope. What else can I match? Come on, play along. We only have one more equation. We wrote a slope equation. We wrote a... Is the displacement suddenly going to change at L over 2 when you cross from region 1 to region 2?
No.
I hope not. If that would happen, you would probably have a failure of your structure. So that means that the displacement in region 1 at x equal L over 2 is equal to the displacement in region 2 at x equal L over 2. See how easy that is? The challenge becomes actually applying those 4 conditions. So for example, let's try this one. Number 1. So I go to what? That's going to be my first region. This is going to be my second region. So I go to this equation. I plug in x equal to 0, 0, 0. All I have left is C2. C2 has to be
0.
Oh, this is going to be easy. C2 is 0. Let's go to this side and plug in x equal L is 0. So I go to my second equation. I plug in x equal, one equation in 2 unknowns, C3, C4. Can I solve that? Not yet. So I'll plug in this guy. So I'll come here and plug in L over 2. That's equation C1 is equal to this one. Plug in L over 2, C. Oh, so I have another equation in now C1 and C3. So I have one equation in C1, C3, another equation in C3, C4. So go to displacement now. Now I already know that C2 is 0, so here's an equation with C1, C3, and C4. 3 equations in 3 unknowns, which would have to be solved simultaneously.
Great.
With symbols. I like Mr. Fazell's reaction to all this. He's just shaking his head like, no way, Jose. This is not home fun. So there's the challenge in these problems. They can be done. Obviously, they can be done. And for any number of regions, we could do it. We've got to always come back and apply those matching conditions. And it causes your conditions to be a little challenging to solve. So I would not expect a problem like this on the exam.
Unless it's Dr. Pease.
Now that I've said that, this particular problem has a shortcut. Do we know something else about this problem in terms of slope and displacement? Do you know the slope somewhere?
Yeah, at L over 2 is it 0? Should we assume that?
We don't have to assume. In this particular problem, since it's symmetric, we know that maximum displacement occurs in the middle, right underneath the load P. That means the slope is 0. So you could come back and say that at L over 2, the slope is 0. You saw for C1. At L over 2, the slope is 0. You saw for C3. And the problem gets a lot simpler. But I don't want to give you the impression that every problem has some little cute little thing like that. This is the only one. If I move that load, if this becomes L over 3 and this becomes 2L over 3, then they can't do that anymore. You don't know where the slope is 0. So keep that in mind. So I'm not going to attempt to try to solve this, obviously. But I wanted to show you. So this is in our... I'll go ahead and stop the video.